So hello again. So we now are moving for the Posicast control journey. This is from video 4. In this case, we are going to continue to speak about the Gantry-Crane control problem, but in this case with the off-cycle Posicast. Okay, I have just introduced the model in the last video, in video 3. And okay, so I'm not going to repeat the two equations, transfer equations. E1 and E2. Okay, you can find the details in this paper, but and so I'm going to move to the next simulation experimentation. So in this case, we got the two transfer functions. We are going to apply a force here in the input and to obtain the displacement of the car, x, capital X, and then we are going to estimate the rotation angle of the suspended load. Okay, so in this case we are going to apply a pulse because this is open loop. This is a pulse just enough to get the trolley to the right position, and you are going to watch the oscillation of the load, the suspended load. So the transfer function for G1 is this one, and for G2 is the other one. So now we got two dampings. One is B2 is the damping coefficient of the suspended load, and B1 is the damping coefficient of the car, the movement of the car. So the first case that we are going to see is just another didactic simulation. We are not considering there is no damping in the movement of the car. So this is the transfer function that you can obtain with these conditions. You can check this in the paper as well. So in this case, we got in the bottom plot the pulse. The force is a pulse, as you can see. And of course, there is no damping, so the car is going to move and not stop the movement. So this can be seen here in the overlapping the cars in the positions, the frames, and you can also see in a kind of video that is interesting to see that the car just goes and doesn't stop. As you can see, it leaves the and so you're going to speed up this. And okay, so the next case is a more realistic case where there is damping in the movement of the car, and this is the resulting transfer function. And of course, in this case, the trolley position moves to it stops in this position here. Okay, so you're going to also you will see here in the video, in this picture, we got in this case the displacement is 1 meter, and this is the overlapping situation. You can see in this case that as you are going to see in another video that the linear approximation of the model is valid. This oscillation of the load, the angle has to be small. So if you see in this case the displacement, you can see here, is going to oscillate a little bit in around 1, as you can see here, and then it stops this movement. And okay, so once more, this is just with a pulse and open loop control. And okay, so now comes the place that we are going to apply the offsite Posicast, to shape this input, this step that we are going to apply to the position of the trolley. So we got the position of the trolley is going to be a step, and this is going to be the shaped signal that is going to be applied to this transfer function that you are going to obtain the oscillation, the rotation angle. Okay, so in this case, we are going to consider in the design of the Posicast the overshoot is 0.52 and the TD is 1.52. 59 seconds. So this, if you just apply this sum in this end of this block, this is the transfer function of the shape signal. So it is equal to this signal, who comes with A1, and then we have to add this component here, who comes with these two, A2 delayed with this part, as we haven't seen in the video, in the previous video. Okay, so this is the transfer functions once more. This HC represents the half cycle, and so we can evaluate A1 using the overshoot, and it becomes 0.66, and A2 is just subtracting A1 to 1 is 0.34. Okay, so this transfer function, the Posicast half cycle, becomes this one. So we are going to use this, and the simulation in this case for this Gantry-Crane system is this one. You can see here the one in blue is the input, so it's this step, and then we got the dashed one, so this is the shaped input here. Okay, this one here, and now you can see here that the movement of the load is going to almost not having any overshoot here. Okay, as we are going to see in the simulation. So once more, this is the initial position, this is the intermediate position H, and this is the final position. And so the Posicast moves the car to this position, waits until it oscillates, and then it reaches the final position. Once more, I'm going to tell you that these oscillations are heavy oscillations, so this is just for illustrating the principle of the half cycle. Okay, I have a video here that I'm going to show you from the simulation, and you can see here this is overlapping the positions, and then when there is the final position, immediately the car goes to ideally to the final position. Okay, and now I'm going to repeat the video, but not overlapping the graphics, so it's the same thing as you can see here, and then it going to move to the final position. Okay, it seems like magic. And okay, so now we are going to see if you overlap, if you have this G1 here to evaluate the angle with a pulse. Now we're going to consider a pulse. The force is going to be 5 newtons. And so if you do this simulation, now we can see here that, okay, now the deflection of the angle is low. So this linear model approximation becomes valid. And you can see here the displacement, okay, with the pulse from the initial position to the final position. Okay, just to, okay, the same thing, but not overlapping the graphics now. It's going to stop in the final position. So just to conclude, okay, this video, we have done some experiments with real systems in several universities in Portugal. One, it was done in Minho University, and so we have published this paper. And these are students' names. This is a student name at the time, this and this, and then we got this colleague from the Minho University, and Filomena Soares and myself collaborated in this project. This was in 2016-17, so this was published in 17 in the Mediterranean Control Conference. I'm going to show you a video about this one, and the other one, it is not. It was in the next year, and it was done with Stefan Vidal. It was a master student. He was supervised by me and Josunaldo, and there are some colleagues also participating in the experiment, and this was also with a robot that I'm going to show you. So if I change now for the, you can find these links in my YouTube channel. I have created a Posicast control playlist. There is one in Portuguese and another in English, and this video is also in this playlist. I'm going to enlarge this, and you're going to see some simulations with the devices that the students have done in the projects. Okay, this is with a kind of device. This is, of course, this S control that you are going to see in the next video. Okay, this is over. It seemed to me that they have more. And okay, with the robotic, this case was to try to see if you can implement with a robot. In this case is UR5. Of course, this is the initial movement of the arm without any Posicast. As you can see, the load, suspended load, is really oscillating, as you can see here. In this case, we are not going to consider to reduce the oscillation, but we are totally, but you can reduce the oscillation heavily with the Posicast control. Okay, this was okay, also interesting, and now with the slow motion. Okay, so okay, this is also, yeah, okay, this is off-cycle Posicast, just with the jump.
I
okay.
think we should explore.
Okay, no, and okay, so with this I conclude the video for. I hope that you enjoyed. Thank you.